Okay, we continue with the third lecture of Professor Ivan Dimitrov, who is talking on root systems.
So, on Monday, I introduced the notion of the quotient generalization. So, R in Euclidean space E with the base sigma is a generalized root system with the base. And taking a subset of the base, I have E decomposes the orthogonal direct sum of EI and E mod I. So EI is just the subspace spanned by I, and E mod I just for consistency is the orthogonal complement. Defining pi I, the projection from E to EI. And the theorem was that R mod I, so whatever I write R mod I, this is just the projection. So R mod I is pi I R. Sigma mod I is pi I of sigma, except for 0, and so on. And the theorem is that R mod I in E mod I, sigma mod I is a generalization system with the base. So, unlike root systems, taking quotients of generalized root systems behaves nice. We still get the generalized root system. Taking quotient is full-tolerable, meaning that if I take subsets I and J one into the other one, then the quotient is the intermediate quotient with intermediate quotients, as in the second or third isomorphism theorem. I don't remember which number it is. Okay. And then as a remark, S in R mod I is the base if and only S is pi I of sigma tilde for some base sigma tilde of R retains I. So this at least tells us. So we had the absolute definition. I stated the classification for rank 2, which I said there were, and I forgot again, 14 or so many irreducible of rank 2. But now this theorem provides us with a consistent way to construct a lot of quotients, because I can start with a root system. Every root system is a generalized root system, and construct also quotients. And this will give me family of generalized roots. Now, this procedure is not recursive in the sense that if in the ones that I already constructed, I construct their quotients, I'm not going to get anything more because of onto reality. Because the quotient of a quotient is a quotient. So in one step, starting with root system, I only get some level. Maybe there are some that are not quotients of root systems, but just for quotients of root system, in one step I get the whole family of generalized root systems.
But I have to be a subset of the stable roots of the root system by which you take the quotient. So the span I would be well, a special root system, a special subsystem.
Yeah.
Of a level.
Yeah,
You
but
cannot take a quotient by the root system, which is not the root system of a value.
no,
For instance, long
No,
roots, you
no.
cannot take the quotient by the long roots.
no. I mean, if I take the long roots, in all cases, the long roots. So as I mentioned last time, this set is just there for convenience. In fact, all that matters is the vector space that it spans. And if I take the long roots, they span the whole space. So I'm going to get a very boring portion.
So in this case, yes, but otherwise there could be something which is not.
Yeah. Okay, so, and I mentioned last time also that there is another portion with respect to a subspace, which gives us the generalized root system. This is the the ones that are obtained by twisting. But I don't have a consistent theory for those. So this is just an example, but all the interactivity, etc., applies under this condition. So it is then reasonable to try and study portions of root systems. And these are very easy portions of root systems are very easy to understand. At least up to equivalence. Up to equivalence means I care about the fine structure when the sum of two roots is the root and so on, but I don't care about the orthogonality properties and angles. And what I mean is the following example. What I have to do, let me introduce notation. That's our user system. So XL is a root system. Irreducible. So X is A, B, C, D, E, F, G, and L is the rank. So for A, it can be anything, any positive integer. For B, it starts from 2 and so on and so forth. For G, it is only 2. For E, it is 6 or 7, 8, so on. If J, the simple roots are alpha 1, alpha 2, alpha L. And I'm going to take the standard label, labeled as in movement here. Why that? No reason. Just you need to choose a label. But I'm so for example for E, I'm labeling them 1, 2, 3, 4, 5, 6, 7. This is the probability labeling. Why? Because. So now I am identifying sigma with just the set 1, 2, L. I'm not going to write out just the indices. For subset J of 1, 2 L, let me denote I that by either complement of J. So this is the set 1 to L except for J. And then I'm going to denote by XLJ the root system XL portion by I. So, and sigma J is the base consisting of alpha J bar, which is 5I upon J, for J and J. So the size of J shows me the rank of this system. That's the notation. And now I'm ready to explain the sentence that they are very easy to understand. So suppose I want to understand F4 to 4. This means I'm taking the root system F4. 1, 2, 3, 4. And I'm taking I to be alpha 1, alpha 3, and portioning F4 by I. So the 2 and 4. You can go and find in many places the list of all roots of F4. I mean, for the classical systems, you have a general formula for all the roots. For the exceptional ones, you have list. F4 is not the longest one. E8 is the biggest one, but it is still manageable. It's a list that fits on 2 pages. And then, in order to project onto the orthogonal complement of the space span by alpha 1 and alpha 3, at least as a vector space, all you have to do is forget coordinates 1 and 3. Read of the roots here and forget coordinates 1. So only read coordinates 2 and 4, and I'm only going to list the positive roots, except for 0. So I'm starting to read here. I read 0, 0, 1, 0. Okay, 1, 0, I record. 0, 0, 0, 1, record. 1, 0, already recorded. 1, 0, already recorded. 0, 1, already recorded. 1, 0, recorded. 1, 0, 1, 1. 1, 0, 1, 1, already recorded. 1, 1, 2, 0. 1, 1, 1, 2. 2, 1. 1, 2. 2, 1, 2, 2. 2, 2. 2, 2. 3, 2. 3, 2. And that's it. So the roots of the system F4 to 4, the positive roots are given by these 8, the strictly positive roots are these 8 roots. This is a rank to generalized root system. It is in the list that I told you about last time. Now, if I wanted to speak of the honest orthogonal projection, I'm not getting to by this, so this is in terms of alpha 2 bar and alpha 4 bar. But this is only up to equivalence. This system F4 to 4 is equivalent to a system with these strictly positive roots. If I want to compute exactly the Euclidean structure, I have to do some explicit calculation of the projections. And in this case, it turns out to be alpha 2 bar is 1, alpha 4 bar squared is 3 halves, and alpha 4 is minus 2. Again, this is not a difficult calculation, a little bit annoying, but just an easy calculation. The interesting thing is that actually, using the classification of the rank 2 root, the generalized root system, I can identify this generalized root system in rank 2. And remember, I had the idea that some of them depend on 2 parameters, actually just one of them. Some depend on 1 parameter, and some are rigid. A2 depends on 2, B2 depends on 1, G2 is rigid. They are more depend on one parameter, but most of them are rigid. And it turns out that this is rigid. So I didn't actually need to compute this. Because when I saw that it is equivalent to that system, there is only one isomorphism class in that equivalence class. Hence, I could have recovered these lengths just by the classification of the rank. But my point is, it is very easy to work with the quotients, at least up to equivalence. Any questions on this? I must say that obviously writing down all quotients is something that nowadays can be done trivially by AI. I have not done it. Before that, it required a little bit of coding. But the truth is, I would say, well, just for the sake of saying that I could do it, within 3 or 4 hours, I could write all of that. So this is by hand. So it is really a very easy computation. It's not some heavy kind of boost of calculation. It's very easy.
All of them for F4 or for?
No, for all roots. For the series, it is I have consistent way of writing them. For the exceptional ones, takes me an afternoon. At the end of the afternoon, I feel I've accomplished something, and then later on, I realize no. Yes. Anyway,
What is the technique you use to classify the roots? Like what methods?
classify it in what sense?
The roots that you're saying for writing down these roots.
To
I mean,
how to write these systems, or
Yeah.
just what I told. I'm looking at some motion. Yeah, this is what. Yeah. Actually, I'm
For these
writing.
ones, it is more interesting. So
Hmm?
for these ones are like this big list that you wrote. Did you do that calculation or is it?
Yeah, I did that calculations, and I'm saying we can do all these calculations in an afternoon by hand. Of course, that would be stupid. You can run it by AI, but so it is a very easy calculation. That's one. Now let me give you an example in a series. What happens up to equivalence. So take, for example, B5. And let me take B5 1, 2, 5. So B5 has roots X plus minus epsilon I plus minus epsilon J plus minus epsilon I for I, J between 1 and 5. They have to be different. Of course, in 0 is also okay. I will get wrong here. Now, if I take sigma here, it is epsilon 1 minus epsilon 2, epsilon 2 minus epsilon 3, epsilon 3 minus epsilon 4, epsilon 4 minus epsilon 5, epsilon 1. And let me know that so I bar the phi of epsilon I, phi with respect to alpha 3, 4. Because I'm projecting onto the orthogonal complement, onto the complement of these. So this means that these two things project to 0. So I'm seeing that D5, 1, 2, 5 would be in terms of epsilon 1 bar, epsilon 2 bar, epsilon 3 bar, which is epsilon 4 bar, which is epsilon 5. It will be in terms of the projections of all the epsilons, but because epsilon 3 minus epsilon 4 projects to 0 and epsilon 4 minus epsilon 5 projects to 0, I get that epsilon 3 bar, epsilon 4 bar, epsilon 5 bar project are equal. And then this would contain, of course, all the expressions of this form. Plus minus epsilon I bar, plus minus epsilon j bar, plus minus epsilon I bar for ij between 1 and 3. I don't need to write 4 and 5 anymore. However, it will contain more. If I look at the root epsilon 3 plus epsilon 4, that would project to 2 epsilon 3 bar. So I have to add here also plus minus 2 epsilon 3 bar. And 0. The 0 is almost. So this is just like B, except one of the short roots comes with its double. In this case, I'm not making the calculation of the length, but what happens is that the length of the epsilon bar and epsilon 2 bar remains 1, the length of epsilon 3 bar shortens. The square of the length of epsilon 3 bar is 1/3 instead of 1, because there are 3 things going down to it, and they are mutually orthogonal. So you can compute this.
Can we write a new version of a dinking diagram where the edges are going to record the lengths of the alpha string through beta?
We could.
So this would give us a new definition of a dinking graph for all of these guys, where instead of recording angles, we record lengths of alpha strings through beta.
Yes, we could do that. The unfortunate thing is that even if we did that, the dinking diagram does not recover. So the dinking diagram has to be adorned by more stuff, not only the edges, but also the vertices. I have to say what the multiples of these roots are roots.
Yeah.
So it will be much heavier dinking diagram, and there is an example where two root systems with the same dinking diagram actually are different. So for that reason, we did not explore it any further. So the nice the comment that I made about root systems, that the amazing fact about the classification of dinking diagrams is that you are saying that I'm considering all Levin subalgebras of Lie algebra. And all I need to know is the rank 1 subalgebras. There is nothing to know there, they are always of 2, right? And the rank 2. And how they interact. If I know this, I know the whole layout. While if I'm thinking of a simplex, just knowing the vertices and the edges doesn't recover the simplex, right?
But that is exactly the case with Nichols algebras. You still write down labels on vertices and edges, and yet nothing is determined from rank 2. You have to go all the way to rank 4.
So we have the similar. I don't know whether we have to.
Okay.
I would trust you that there is a maximum rank. So what I'm going to state later as a theorem makes it plausible that I don't have to go all the way up to rank n, but say stopping at rank 4 would be sufficient. And I can see how it would fall from here.
Okay.
I cannot prove it, but I can tell you why that would.
Okay.
But you cannot stop it right. Any questions so far? No. Okay. So this is what I'm going to do. And now I want to list. I want to list further properties. So, Rita and I made observation. That every irreducible rank 2 generalized root system is equivalent to XLJ for some LNG. So the rank 2 in our classification, when I told you that there were 14 of them or 16, I keep forgetting. All of them are actually portions of root systems, at least up to two. Obviously, they are not isomorphic because in the portions of root systems there is some rational. These the Cartan matrix, if I consider as Cartan matrix just the matrix of the inner products, it is rational, and I allow any reals there. But if I restrict to rationals, they are almost exactly the quotient. I don't want to say more about this. Because of this observation, and also noticing that there are close relations between what happens in rank 2 and some other relationship between things other people have been studying in the context of hyperplane arrangements and defined value points. We actually conjectured that this is true in general, that every reducible generalized root system of rank greater than 2, greater or equal than 2, rank 1 does not work. Rank greater or equal than 2 is a quotient of root system. And it was quickly proved by, this conjecture was quickly proved by Kuntz and referring to our German educated or trained colleagues, how do I pronounce this name? That's not Müller.
Yeah.
Okay, whatever Bob said. Constant, whatever Bob said.
It is two words, one
Yeah.
is will and the other one is care. And the will should be with a longer u because of the ratio.
Okay, so every irreducible generalized root system of rank greater or equal than 2 is equivalent to XLG.
Did they use something longer maybe?
Yes, they use a classification of these value points. And the truth is,
The viable points you define?
yeah, but they have a different definition, which is intrinsic. So the point of this picture that I'm building is there were value points that were defined intrinsically. There are crystallographic hyperplane arrangements that are defined intrinsically. And of course, with both of them, there are some root systems. But the root systems were the root systems of those. And you could not define axiomatically what these root systems are, rather than point to these root systems. And one of the reasons is that if you're looking at hyperplane arrangements, there is no reason to have multiples of roots being roots, because you're taking just the orthogonal hyperplanes. But then if you don't do that, you're escaping nice axioms. And so I think of these results in one way as the counterpart, which gives you intrinsic definition of these objects that are the counterpart of value points and hyperplane. type of what groupoids, which are they call biogroupoids, type of hydroplanary units, which are called crystal. And the classification of biogroupoids on which this proof is based is actually somewhat unsatisfactory. Not my opinion, but the opinion of one of the authors of that classification, because it takes uses heavy computer aided computation. So there are some cases that cannot be presented without. Based on that proof, the proof of this theorem is rather straightforward. But the difficulty in proving this theorem is actually in the classification of variable points.
And then when we need to include the multiple of proofs, it doesn't change.
Yeah, and see how this affects.
Yeah.
Okay, so this is in some sense nice result, in some sense unsatisfactory, because nice because it's a classification theorem, unsatisfactory because when you define a new object, you hope to have some new examples. But here we're not getting the example. Okay. I want to complete this hour with actually it's quite a bit of time this hour, but so I want to continue then by some remarks on portions of books. And hopefully I'll convince you that they're nice and useful. And I'll mention how cost control systems, apart from helping us improve some results in for different applications, which I'm not going to speak about today, explain something that for a long time mystified me about the even the classical. So, so the first result that I want to mention, so far I have told you that if you want to consider generalized root systems up to equivalence, it is sufficient to take just quotients of root systems. But you don't even need to take quotients of all root systems, because the first result is that every root system is a quotient of a simply length root system. Is in all my statements means is equivalent. However, in this case, actually, one can show that this is more. This is more. And because of the functoriality, if I'm considering quotients of root systems that are not simply laced, they themselves are quotients of simply laced. So the ones that I substitute are also quotients. So I can really work only in the realm of simply laced root systems and quotients. I will go.
That's how in our field also, people prove things for simple list and say that for the non-simple list, everything follows by folding argument.
But that's not folding.
No?
That's not folding. That's a different construction. The folding is, yes, it works. And and it is quite explicit. However, as we then pointed out, I also gave a realization of the following as projections, but not projections of the type that I consider. And they are messy. So, for example, it's more difficult to recover positive systems and so on, because in the forex you are not preserving the base of the simple roots and so on. This is a different construction from the forex, and in which actually you're preserving and you can apply inductive formulas and so on. So this is a different construction from the forex. The second remark is the other source of possible root systems is root systems of classical Lie superalgebras are portion roots. I don't need to specify here whether they are portion root systems or simply Lie, because if they are portions of any root system, then they are portions. One has to be careful here. Are equivalent to here equivalent really is important because these root systems of the super algebras come with a natural form which is not positive definite. And in the combinatorics that I consider here, the form is positive definite. So this is not, when speaking of the root, this is not the same form, and a lot of the properties are lost. For example, if I want to preserve the Z2 grading, I have to add additional information for the Z2 grading and be careful how it interacts with the quotient root system structure. But at least combinatorically, for example, in superalgebras, when you study representations, one unknown fact is that there are many Borels, and the Borels are not conjugate, and they look very much different from each other. This identification allows us actually to consistently work with these different Borels and write down what these different Borels. So this is useful.
So they're equivalent subsets of vector spaces with the
Yeah. So all the reflections defined, I'm not sure whether they were first, but they were defined and extensively used by Sergambo and Penkov, exactly these reflections that we defined are the now, I want to mention the explicit list, and this is a nice and important statement. Portions of AL and BL. Because I already said that every quotient root system is every root system is a quotient of simply Lie, so I'm only considering the simply Lie. And if I consider AL, the roots are epsilon 1 minus epsilon 2, epsilon 2 minus epsilon 3, epsilon n minus epsilon L minus epsilon L plus 1. These are the simple. And the roots are plus plus minus epsilon I minus. With a slight additional notation, I can, with a slight additional notation, I can write phi I have epsilon I as epsilon I bar. Because in the space in which the roots live, there are no elements epsilon I. The elements epsilon I live in a space of one dimension high. The roots, the space span by roots is coordination one. But this is not very difficult to justify. Then alpha equal epsilon k minus epsilon k plus one in I implies that epsilon k bar equals epsilon k plus one bar. Right, this is what, and then this means that the projection phi I just bunches, puts epsilon I, epsilon 2, epsilon n in different blocks. Meaning that if I'm projecting, for example, I can have epsilon 1 bar equal epsilon 2 bar, epsilon 3 bar equal epsilon 4 bar equal epsilon 5 bar, epsilon 6 bar, epsilon 7 bar, epsilon 8 equal epsilon 9 bar. This would be if alpha 1 is in I, this is if alpha 3 and alpha 4 are in I, this is if alpha 8. So I can think of these as, say, the first block is delta 1, the second is delta 2, the third is delta 3, delta 4, delta 5. And then ALJ will be 0 plus minus delta I minus delta, let's use delta A minus delta B, for A, B, A not equal to B, between 1 and something, the number of blocks. So this means that all quotient of AL are actually equivalent to 8. So AL is close to this is the reason why the symmetric group, all the symmetric groups put together have a structure of an operand. You can take a bunch of elements of symmetric groups, different symmetric groups. So one element of symmetric group of k elements, and then k elements of other symmetric groups, say S1, S2, Sk, and make an element of the symmetric group of the sum of the S's. How? You're going to think of each of the pieces as blocks. You're going to permute the blocks by the outside one, and each of the blocks you're going inside in the block to permute it by its corresponding kind. This is like shuffling cards. You take, say, deck of cards, split it into 3 parts, shuffle each piece, and then shuffle the 3 pieces together. This is applying an element of S3 to elements of corresponding symmetric groups. This gives an overall structure. The reason for, I'm not saying that the reason for having this overall structure is this fact. But one may ask, can I do this with the vowel groups of type B or the vowel groups of type G? And it's not quite the case. And the reason for that is that we do not have the quotients of type G still of type.
Just to make sure these E's are epsilons.
Which ones?
The EG.
Yeah, these series are epsilons.
Yeah.
Thank you.
That's fine. We know.
Yeah. Now, let me look at the same picture for GL. What is the deal? What happens in this case is that we have EL is the root plus minus epsilon I plus minus epsilon J for IJ between different IJ between 1 and L. And this is the thinking diagram. And again, alpha equal epsilon k minus epsilon k plus 1 in I, if I start projecting, or give me epsilon k bar equal epsilon k plus 1 bar. But I have to be careful here because I have in the beginning I don't have a problem. However, towards the end things may get a little bit towards the end things may get a little bit more annoying. If I have both end roots in I, if epsilon n minus 1 minus epsilon n and epsilon n minus 1 plus epsilon n belong to I, this would imply that epsilon n minus 1 equals epsilon n minus n bar equals 0. So I have to actually consider two possible cases. DOJ. The first case is if not both epsilon n minus 1 minus epsilon n minus 1 plus epsilon n belong together. So one of them is right. Then what happens is none of the projections will be 0. And I'm still going to have the roots in the form of this form with projections. Right? Which should give me DOJ is 0 plus minus epsilon I bar plus minus epsilon J bar. Let me use the delta. Delta A bar plus minus delta B bar. Yeah, no, actually, it turns out that was all about that we have 4. Thank you. So now, not only did I forget to turn off my phone, but also when I hasn't been paying attention, I would scroll, you were sending message. Okay, so edit out this from the video. So I will have all these tools. And for A, B, between A and T. Right? But whenever I have a root in I that identifies two consecutive ones from their sum, epsilon k plus epsilon k plus 1, this would project to epsilon k bar. So some of the roots will actually come with doubles. Plus minus 2 delta A for A, but not all of them. Just some of them. The ones that correspond to blocks. So the blocks that are single element do not double, and the blocks that are double element double. I'm going to denote it by D. I'm going to denote this root system by how do I denote it? By D. TS. This is not a canonical notation. I welcome suggestions for better notation. I'll explain why I chose this one. So this is G because I have all the roots as in D, and S because I have taken the doubles of S in the roots. Here S is between 0 and D. However, if in case 2, where both epsilon n minus 1 minus epsilon n and epsilon n minus 1 plus epsilon n belong to I, then DLJ would have 0 as a root, would have delta A plus minus delta J and delta B. But because I have projections to 0, it would have also plus minus delta 8 entry. For example, epsilon k minus epsilon n projects here to epsilon k bar. Because epsilon n bar is 0. So I'll have all the roots as in these. And again, because of books, I am going to double sum. And I'm going to denote this system by BTS. So the quotients of A are all just of type A. The quotients of B, however, of G split into two families.
Sorry, but S is integers between 0 and T or equal?
1 and T. S is between.
No, I said it would be above that. We have a DTS and then S between 0 and T.
A is between A and S. Sorry. Here?
Yeah.
Yes, S between zero and T,
It can be zero also.
it can,
So in this case, the second part with the two.
it's not there.
All right.
This is if I do not quotient, if I start with D and I just do D. Yeah, so. Yeah. And here, again, S is between zero and T. And let me show you what the boundary is, and this is the only argument I chose these notations D and B. And again, I'm open for suggestions. If I take D, T0, this is just dt. If I take dtt, this is ct. If I take bt0, this is bt. And if I take btt, this is bct. Remember, from the very beginning, I've been advocating that this is the enrichment root system and should not be discarded. So these are the endpoints. Questions or comments? So this means that in my very vague discussion of the possible operand for type D, for example, as analog of type D, if I want to make an analog for D, I have to include all of these portions in the whole family. So I have to be taking somehow the not just the vowel groups of or the analog vowel group for the root system D, but whatever the analog vowel group is for all these portions. And that is why it is more.
But if you take the root system, the product of root system of D and B,
Mhm.
and then you take product of the root system
D,
D and B,
YB,
then you have the quotients, which will be in the B part,
but why
from
not?
the quotient of B.
Yeah,
Like in
but,
terms of operand
Ah.
mentality.
well, no, but I hear, yeah, but this outside thing is in the quotient, the inside are in the subs. If I think of these, if I think of this, in the opera sigma of tau one, tau two, tau k, for permutations, these are the permutations of the pieces of the deck, and this is the permutation among the, these are within each subdeck, and this is the permutation of the decks. This is in the quotient. These are in the subs. So here I have to include all of these, and they are kind of, they can get, there isn't much of a problem here, actually. At least when I speak of reflections, because the fact that I have all the short roots and some of the doubles do not affect reflections. But here, I do not have any multiples of these roots and I imagine them, which increases the analog of the value. So it really gets sense. And in fact, this actually explains another phenomenon that I have seen in combinatorics. A lot of results that go for type A, go for type B and C, but do not go for type D. Why? Because the type B, which is this, it's further quotients. So B is BT, B is BT0. So already for B, I have taken a quotient including the last two roots. So if I take further quotients, the last two roots will still be included. So the quotients of type B will be of these types, which only double some existing roots. In terms of reflections, it doesn't give me more reflection. So even though a little bit more complicated, still there is inductive picture for type B. and type B and C are basically the same. But for type D, I have to go this whole hierarchy of how many roots, of how many roots of the form 2 delta A appear. I can have none for D, or I can have all of them for BC, and in between everything else.
And there is a plus minus there of the first, the BTS. The roots, there is one of them which has only a plus and no plus minus.
No, everything can be plus minus.
Okay, so the second listed root in BTS. BTS,
Yeah,
the definition of it, the second listed root after the zero.
uh-huh.
Mhm.
Oh, okay. So this is the comment about the quotients of D. So even for the classical ones, we have a whole hierarchy. I expect they do appear, they're very kind of prominent appearance in the Nichols algebras. Because this is a whole new hidden kind of classical hierarchy, which we don't see otherwise. Before I stop for a small break, the exceptional ones, I'm not going to making remarks on them. In this paper with Rita, we have extensive tables that I think would be useful. Just as a curiosity, G2 is a quotient of E6, E7, E8. It is quotient of all three of them. F4 is a quotient of E7 and T8. G2 is also quotient of F4, but it's not interesting because G3, the exceptional Christopher algebra, is a quotient of P8. And F4, the exceptional is E8, again. No, E7. I don't read my notes. And G1 to alpha is the quotient of D4.
When you say that it's not interesting that G2 is a quotient of F4?
Because F4 is a quotient of E7, and if you see what the quotients are, you will recover it from there. However, from what I have written, it's not obvious. Yeah. I think it's a good time to take a bit of a break and then continue on. Well, with the two consecutive ones, I think it's